All right, so today what we're going to do is we're going to take a look at a linear function in context. And so what we're going to do is we're going to read the problem first and decide what is the important information. So we've got Seabreeze offers its customers an admission option to purchase a spectator pass for $10 and buy $2 single ride tickets for each ride they ride. So we've got two bits of information. So everybody who comes has to pay $10, and then they ride for as many tickets as they buy or as many rides as they ride, they have to pay $2 more. So we know our x-axis is going to be the independent variable, or the number of tickets that they buy, and our y-axis is going to be the dependent variable, or how much total they spend. So if they don't ride on any rides but just enter into the park, they're going to get 0 tickets, and they're going to still pay that $10 admission price. If they buy 1 ticket, then they're going to pay an additional $2, so 10 plus 2 gives us 12. 2 tickets would be 14, and so on. You can see that our rate of change is going to be $2 for every 1 ticket. All right, so now we've made a table. Now let's go to the equation. Since we know it's going to be slope-intercept form, we know that it's going to be y equals mx plus b. Our b is our y-intercept, so I'm going to start there. Since we know that for 0 tickets, or when x is 0, y is 10, we know that b is going to be replaced by 10. Now, we also know that our slope is 2, because remember, for each ticket that we bought, it went up $2. So we're going to put our slope as 2. We could also replace y with f of x if we wanted to, if we wanted it in function notation. Now, here's a look at the graph. We've got the number of single ride tickets on our x-axis, just like in our table. We've got the cost on the y-axis, just like in our table. Now we could graph this two different ways. We could either plot our ordered pairs. 0, 10 is right here. 1, 12 is right here on our graph. 2, 14, and so on. Or we can use what we know about slope-intercept form. So here we know the y-intercept is 10, so we start at 10. And then we know that our slope tells us to go up 2 over 1. Now even if that doesn't look like up 2 over 1, if I look at the labels on the graph, I can see that from 10 to 12 is 2 and 0 to 1 is 1. So even though the size of it looks a little odd, as long as I use my labels, I'm good. And so from there I can go up 2 over 1 again. Now, why didn't I connect the points? So let's think about that. Can you have part of a ticket or a number like $11 in this situation? No. So the only things that we really want on there are those ordered pairs. All right, so let's talk about sorry about that, that needs to go away. So what is the domain in context? So the domain is going to be the y value, or the x values. So if we look back on our table, the x values are 0, 1, 2, 3, 4. They're going to be the integers and 0. So how I'm going to write that is as a list of numbers. So we've got 0, 1, 2, 3, and then I'm going to keep on going with the ellipses, the dot, 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 to say you could keep going. Now, can you keep going forever? Probably not, but we don't really know where the end point is. Now, what is the range in context? So here, we want to know that that's the y values. So I can look back on my table, and my y values are 10, 12, 14, and so on. So again, I'm going to write that as a list, starting with 10, 12, 14, and so on. Now, so that my handwriting was a little messy here, so I wanted to show you what it would look like with the kind of brackets. So is the function continuous or discrete? Well, we already sort of talked about this over on the graph. Continuous means that it's going to be measurable. So things like distance and time, things like that are measurable. Discrete means, I'm sorry, I'm fighting with me here. Discrete means that it is countable. So continuous is measurable. Discrete is countable. All right, so are our variables measurable or countable? So let's think about this. If we're talking about the number of tickets, we're going to count 0, 1, 2, 3. We can't have part of a ticket. And the same thing with the price. And remember, we talked about when we graphed on the graph, we didn't connect them because the values in between don't make sense. So both variables are things that we count. So we're going to say that this is discrete. Okay, so y, again, you can't have part of a ticket. Is the function increasing or decreasing? Well, let's think about it. The more rides that you ride, the more you pay. Okay, so we're going to say that it is increasing for the number of tickets that you buy. All right, now, can we have a maximum? And a maximum is always talking about the y values. So can you have a maximum cost? Well, technically, yes. Eventually, you either run out of money or the park closes. But in this case, we're going to say there is no maximum amount to spend. What's the minimum? Well, remember we said that no matter how many rides you ride, you have to pay $10. So the minimum is going to be $10. All right, so I fixed our slide here for a little bit. So I put the maximum in the right place. We said there's no maximum number for the cost. Again, in real life there would be. And then what is the minimum in context? There actually is a minimum because everybody has to pay $10 to be admitted. So $10 for admission. All right, let's go back up to this last question. Is the function increasing or decreasing? So as you can see, by the table, it's the y values are getting bigger, and by the graph, the y values are getting bigger. So in context, that's going to be they're increasing as the number of tickets sold happens. All right, so that's a brief overview of our linear function in context. Thanks, and I'll see you again.